Welcome to the second lecture in the How to Build and Train Your AI Model program, sponsored by Houston Community College and my nonprofit InspiredK.org. So today, we are going to be covering an overview of what is deep learning, including its subfields as well as how it works, what are recurrent neural networks, or RNNs, which are a type of deep learning method that allow us to have sequence generation and classification, as well as how these recurrent neural networks work so we can understand how to build one ourselves, as well as the different applications of RNNs, such as music generation, which we will be doing in the lab associated with this lecture. We are going to start with some different slide decks from the MIT Introduction to Deep Learning course taught by Drs. Alexander and Ava Amini. So first we're going to start with this first slide deck from Dr. Alexander Amini with an introduction to deep learning. So first I'd like to start with a visualization of the progress of deep learning as it has started from 2015 until now. So on the left here, we can see an image generated by the first state-of-the-art vision model that was able to generate images of faces. And we can see that it is in black and white of a somewhat low quality. And then in 2018, we see another image that has now more color and is more realistic and seems to almost be real. Now in 2020, the MIT Introduction to Deep Learning team created a video of a deepfake of President Obama in 2020 to introduce their course. And this video was about 2 minutes, and it took 2 hours of professional audio recordings for the voice of President Obama speaking, 50 hours of high-definition video to have the movements of President Obama as well as the video itself and the background, and over $15,000 to train a model on all of these audio and video recordings, as well as allow it to generate this 2-minute video from a static predefined script without any text generation, only simple script that was already written by the instructors of the course. So now in a few years, we're in 2025, and I would like to provide an example of what we can do. Hello, AlphaGPT. Can you please briefly introduce yourself?
I'm AlphaGPT, a friendly and supportive AI tutor designed to help K-12 students learn in a fun and engaging way. I can answer questions, explain concepts, and guide you through different subjects in a way that makes sense for your level. Whether you need help with homework, want to explore new topics, or just have a curious question, I'm here to help. What are you learning about today?
Can you please give me a brief overview of what artificial intelligence is?
Of course. Artificial intelligence, or AI, is a branch of computer science that focuses on creating machines that can think, learn, and make decisions like humans. AI systems use data, patterns, and algorithms to solve problems, recognize speech, translate languages, and even drive cars. Some AI, like chatbots and virtual assistants, can understand and respond to human language, while others, like self-learning robots, can adapt and improve over time. AI is used in many areas, including healthcare, entertainment, and business, making life easier and more efficient. Would you like to explore a specific AI topic?
Could you give me a quick overview of recurrent neural networks?
Sure. Recurrent neural networks, RNNs, are a type of artificial neural network designed for processing sequential data, like speech, text, or time series data. Unlike regular neural networks, which process inputs independently, RNNs have loops that allow them to remember previous inputs and use that information when making decisions. This makes them great for tasks like language modeling, speech recognition, and predicting stock prices. However, standard RNNs struggle with long sequences because they tend to forget earlier information. To solve this, advanced versions like long short-term memory, LSTM, and gated recurrent units, GRU, were developed to better handle long-term dependencies. Would you like a deeper explanation or an example?
That's okay, thank you.
You're very welcome. Let me know if you ever want to explore more topics. Happy learning.
So this was my AI tutor that I built for K-12 students called AlphaGPT. And in addition to AlphaGPT, I built a more complex tutor called BMO, which if you watched the introduction video to this course, I used as a assistant to help me teach and answer questions. So be sure to stay tuned until the last lecture of this course, where I'm going to be giving an overview of how I built AlphaGPT as well as my assistant BMO. Now that we've heard an overview of artificial intelligence and recurrent neural networks from AlphaGPT, I'd like to give a more in-depth overview of artificial intelligence, machine learning, and deep learning. So artificial intelligence is the overall field that contains all and any techniques that allow computers and machines to mimic the behaviors of human intelligence. Then a subfield of artificial intelligence is machine learning, which is the ability of allowing computers and machines to learn to do a specific task without being explicitly programmed to do this task. So for example, if you have a mailbox with a lot of different emails, machine learning would be taking some of those emails and sending them to spam, so the program that you view your emails on will be able to filter out the emails that you shouldn't have to read and keep the ones that you do want to read. Then the subfield of machine learning that we're going to be covering today is deep learning, which is the method of having machine learning done through a method called neural networks. And deep learning is called deep because it has many different layers of these neural networks, which are inspired by the architecture of the human brain, and all of those layers make a neural network deep. So overall, deep learning is the ability to teach computers how they can do a task directly from a given input data. So the labs that are going to be associated with this lecture, as well as the lectures in the future, are adopted from the MIT Introduction to Deep Learning course, and they come in both TensorFlow and PyTorch, which are two AI libraries that are extremely powerful. TensorFlow was created by Google and has had a long base and wide supporters, while PyTorch was created by Meta AI, and it is still up and coming but has a fast growing and active community to support. So now I would like to cover why should you be using deep learning and why should you be doing it now, as deep learning has existed since the mid-1900s. So deep learning is especially useful because with other methods of machine learning, the features that are learned have to be manually engineered by humans, which can be extremely time-consuming and will occasionally break if new data is shown that doesn't match the given features. So deep learning allows us to learn those features without having to manually define them from given input data. So it does this by first taking the low-level features, which for an example of facial recognition would be the different lines and colors of a face that allow it to have curves and eyes and noses and all of the other shapes that make up a face. Then the mid-level features, such as the eyes, the nose, the ears, the eyebrows, the mouth, all can be learned based on those low-level features that make each up to have each part of the face represented as a feature. Then the facial structure as a whole is considered a high-level feature, which contains all of the mid-level features together to provide the full image of the face. So deep learning is especially useful as all of these features are automatically learned from given input data of faces, whereas in other methods of machine learning, the low-level feature, all of these features would have to be engineered by hand, which can be very time and efficiency consuming, leading to it not being practical in actual large-scale applications. So neural networks and deep learning have been used since the 1950s, where a method called stochastic gradient descent allowed us to create the first neural network. So now, fast forward about 70 years, we have many more advances that make neural networks and deep learning much more possible and easier to use. So first, there is a large amount of data available. And so all of these datasets that are available are also much larger in their scope. And additionally, these datasets are now available for machine learning and artificial intelligence, so they are easier to gather and store. So for example, we have the ImageNet database, which contains many different images available for training of image AI models, and Wikipedia is a large collection of text generated by humans that can be used to train different large and neural networks. So second, we also have massive advances in hardware, especially the graphics processing units or GPUs that are now available from many different companies. Additionally, these GPUs allow us to parallelize different operations, making the training and generating costs of all of these neural networks extremely fast and cost effective. Finally, we now have new software, including improved different techniques that make machine learning models and deep learning models much easier to implement, as well as new types of models that are more efficient and have higher accuracy in practical uses. Finally, there are now many toolboxes available that you can use to put together a neural network or deep learning model as easily as Lego bricks, such as TensorFlow and PyTorch, which we use in this course. So now that we've covered why deep learning is so important, I'd like to give the most fundamental building block of deep learning an introduction, the perceptron. So the perceptron contains one single neuron that maps different inputs to an output. And it does this by first taking the inputs from a given x1 till xm, with each input having its own assigned weights, which is a list of different values that are matrix multiplied by these inputs and summed together in order to achieve a output that we put through a nonlinear function, which gives us our output in a binary format. So this can be mathematically represented by having each input multiplied with its weights, and all that multiplication being done for every input and its associated weights, and then that output being sent through a nonlinear activation function called g to achieve our output. So in addition, there is another part of the perceptron that can be added, which is called the bias. This is usually set as a weight 0 or W0 and is added in order to make sure that we can shift our inputs one way or another, so that way our machine learning and deep learning model does not cause issues that are usually caused without having a bias. So this bias is added after the sum of all of the multiplications between the inputs and the weights, and it is passed through the nonlinear activation function with our sum of the inputs and weights. So in another mathematical representation, instead of having a sum of each input multiplied by its weights, we can use the format of two matrices of the inputs. So one matrix of the inputs and another matrix of the weights, and matrix multiply those two matrices, the x and w for the inputs and weights, and add the w0 value of the bias and send that through the activation function. So now I've been mentioning activation functions a lot and nonlinear, so I'd like to now cover what activation functions are. So these activation functions allow us to spread the large value that can be any real number that we get from our summation, and it is done to flatten it between a value of 0 to 1 or -1 to 1, depending on the activation function you use. So as an example, we can use the sigmoid function, which has a sort of S shape that maps any value it is given from a value from 0 to 1. This allows us to output different binary values or probabilities for a simple perceptron. So some common activation functions that we use are the sigmoid function, but we also sometimes use a type of method called the hyperbolic tangent, which is similar to the sigmoid, but now maps things between 1 and -1, and is more useful if you want to have a 1 to -1 distribution for other types such as classification or generation. It has a similar shape to the sigmoid function, but does seem to be more stretched out with a higher slope in the middle compared to the sigmoid. Finally, another common activation function we use is the rectified linear unit, or ReLU for short, which is extremely simple as it only finds the maximum between a 0 and an input value. And because of the simplicity, it is extremely efficient in practice, but also allows our model to have non-linearity, which makes it very common, one of the most common used activation functions. Here in gray, we can also see many different code blocks that allow us to implement each of these functions. So in TensorFlow, we usually use the tf.math extension and then have our activation function at the end. So for sigmoid, it is .sigmoid. For hyperbolic tangent, it is tan h. And for the ReLU, it is .ReLU. It is similar for PyTorch, where we have torch dot and then the name. So we have the sigmoid function as .sigmoid, the .tanh function for hyperbolic tangent, and finally .nn.ReLU for our rectified linear unit. So now you may be wondering why we need nonlinearity in our different applications of neural networks. And this is because most data that we encounter today is in fact nonlinear. So as an example, let's say we want to build a neural network to draw a line that classifies green from red points on this two-dimensional plane. So if we have only linearities in our network, we'd only be able to have a line that separates these two values. And as you can see, with the best line of fit with only a straight line, it is very inaccurate, and the green and red points are still very mixed. However, with nonlinearities, we can now have much more complex lines and categorizations from higher accuracy. So with nonlinearities, we can create a complex shape that allows us to much higher accuracy categorize the green from the red points. So now, as an example, using our perceptron that we previously defined, we can have the bias set to 1 and two inputs of 3 and -2. If we put this through our mathematical representation, we can see that we get outputted a line in a two-dimensional space, where on the x-axis would be x1 and on the y-axis would be x2. So this would be 1 plus 3 times x1 minus 2x2, because the weights times x1 is 3x1 and the weights times x2 is -2x2. So when we plot this line, we can see that we get a line on the xy plane for x1 and x2, and we set it equal to 0 so we can plot it. And if we have a new point, we can put it through our perceptron and see we get an output of about 0.002, and it is to the left of the line. So based on this trend, we can now make the assumption of categorization that anything to the left of the line will be, when put through the nonlinear activation function, will have a value of less than 0.5, whereas anything to the right of the line will have a value greater than 0.5 when put through the sigmoid function, which allows us to have a probability distribution where to the left of the line will be less than 50%, whereas to the right of the line will be greater than 50%. Additionally, anything that is directly on the line will be 50% exactly, or 0.5. So now I like to illustrate how we can combine different perceptrons in order to build neural networks with several different neurons. So we have our perceptron, which is set with the inputs, the weights, the summation of the matrix multiplications, the nonlinearity, and finally the output. So let's simplify this for our usage and combine the summation as well as the nonlinear activation function into this red dot with a z and an arrow giving us the output based on z. Additionally, we can abstract away the bias term, as it will be assumed from now on that we are automatically adding the bias. So now we have our inputs from x1 to xm sent through this given operation z, and then that z output value is sent through the nonlinear activation function to achieve our output of y. So now all we have to do is just add another perceptron to make a multi-output neural network. So we still have our given inputs from x1 to xm, but now all of these inputs are sent to two values each, the Z1 neuron and the Z2 neuron. And each of these perceptron neurons has their own output. So because all inputs are connected to every hidden neuron, this is called a dense layer, as everything is densely connected. So we can change our previous mathematical equation to now take an input of a given value I, so that way we can have the weights set for each neuron for each input and each neuron independently. So the weights for our first Z1 neuron will be different than the Z2, and the bias will also be different for both as well. So to represent this multi-output perceptron in code, we have built-in layers called dense in TensorFlow and linear in PyTorch, so that way we do not have to implement all of this by ourselves, and we can simply use this defining how many outputs we want to have. So in TensorFlow, this is done with tf.keras.layers.dense. If we want to have two outputs like we have in this diagram, we set units equal to 2. In PyTorch, we use the nn.linear and have the in features set to m, which is how many inputs we're going to have, and out features set to 2, which is how many outputs we're going to have. So if we want to add more layers to our network, we can now add more neurons and create a hidden layer. This layer is called hidden as we only see the inputs and the outputs. We don't always see the computation between the different inputs and their weights. So now we're going to have different weights from the input to the hidden layer, as well as different weights from the hidden layer to the output. So we can now introduce a new equation, one for the hidden layer and one for the final output, where the hidden layer will be with the first weights matrix for each input, whereas the final output will be with our second weight matrices. It'll also have the activation function called on each hidden layer neuron, and the activation function called on the entire output of this hidden layer state, as well as the inputs. So this introduction of the multiple nonlinear activation functions will allow us to introduce more nonlinearities into our network, which will give us higher accuracy in the future when we want to have many nonlinearities for classification or generation tasks. So let's take an example of this Z2 neuron that is taking inputs from all three inputs, from x1 to xm. And each input also has its own associated weights. So first, we're going to take our bias term, which is not shown in this diagram. As I previously mentioned, we're going to not have this bias term. It will be there without having to show it. Then we're going to matrix multiply each input by its associated weights and sum all of the values that we get. Then, in combination with the other neurons, we're going to take all of those neurons' outputs and send them through the activation function in order to achieve our outputs of y. So now that we have understood this multi-output perceptron with a hidden layer, let's take away all of the arrows and replace them with a square and an x so we can represent it more cleanly in the future. Additionally, I'd like to note that we can also have different texts and code blocks to create this multi-output perceptron in code without having to define it ourselves mathematically. So we can use in TensorFlow the tf.keras.sequential object, which allows us to chain together multiple layers and have a dense layer with n neurons, which is our hidden layer, which goes from z1 to zn, and then a dense layer of output 2, as we only have 2 output neurons. In PyTorch, we can do something similar with nn.sequential, where we have a linear layer for our inputs, which are shaped m by n for the inputs by the hidden layer. Then we have a ReLU function, so we can map our hidden layer outputs with the nonlinear activation function. And finally, a linear layer to have our 2 outputs with n inputs and 2 outputs for our two output neurons. So a deep neural network takes this idea of having a single hidden layer and now adds many more, which is what makes it deep. So all this introduces is a new variable k, which allows us to identify which layer we are talking about in the computations. So since we previously had a weights matrix for each of our inputs from the previous layer, we're now going to have much more for each layer and each hidden layer in our deep neural network. So this can be implemented in code by adding many more dense layers in TensorFlow, so we can have all of the dense layers mapped to each other. And in PyTorch, we add many more activation functions of ReLU, so that way each activation function can immediately chain to its output to the next and to the next until we reach our eventual output. So now that we understand neural networks at a deep level, I'd like to cover how we can apply neural networks to a given problem. So let's say you are taking a class and you feel unsure about the topics and you would like to know, will I pass my class? So let's start with two inputs of the number of lectures from the class that you attend and the number of hours you spend on the final project, which is what gives you your grade. So let's say that we have data from previous students who may have passed or failed, and we can see a general trend that the less lectures and less hours spent on the project, the more likely they are to fail, which is why they are in this lower left corner, whereas the more likely to pass will be with more lectures attended or more hours spent on the final project, which will allow you to pass. So I noticed that we have a notification in the chat where we have a question of what is the use of adding multi-dense layers? So the reason that we have multiple dense layers is because if we have many different nonlinearities throughout each layer, then we will be able to understand more features about our inputs. So the more layers that we have, the more we will be able to understand underlying features about our data set, as well as having each hidden layer have its own new contributions. So each layer will contribute its nonlinearities as well as its mathematical computations to the final output. So the more layers you have, the more nonlinearity, meaning the higher accuracy you're going to have in your output. Again, we have the problem of will I pass a given class, and we have our data of the number of lectures attended and the number of hours spent on the final project. So let's say we have this purple point of you who attended 4 lectures from the class and is planning to spend 5 hours on the final project. So let's say we have built out our neural network with 2 inputs for each the number of lectures attended and the number of hours spent on the project, a hidden layer with 3 neurons, and a single output of a probability of how likely you are to pass. So now our model has predicted a probability of 0.1. However, in reality, you definitely passed because, as we saw from our previous graph, you are in the passing area that has a likely trend. So I'm going to ask in the chat why this may be. So if you have any ideas of why the model is so inaccurate about this prediction, you can go ahead and answer in the chat. So I'm seeing an answer that we do need to adjust the weights, which is correct because the process of training our neural network is allowing it to understand the difference between its predictions and the actual expected outputs. So that way it can see how far it was from the actual answer and take a step towards having better answers, which is done by adjusting the weights. So thank you, Mr. Alex, for answering the question. So to perform our training of the neural network in order to increase its accuracy, we are going to use a value called the loss. So the loss is any function that allows us to compute the difference between the predicted value and the actual expected output. We can use this loss value so that way we can go back to our weights and change it in order to minimize the loss. So I'm seeing in the chat that we have a question about first training the model, then getting the weights and using those to train the model. So that is correct. So we are going to get our loss value, then train the model and adjust the weights. So we're not going to collect them per se. We're going to adjust them as they already are. We're going to change them in a small step towards the better direction. And then we're going to go back through, recalculate the loss, and then keep going in a cycle of fixing the weights, getting the loss, fixing the weights, getting the loss for a given set number of iterations. So that way we can have our neurons and our neural network as a whole have a higher accuracy in its predictions. All right, so there are two different types of loss. So for our problem, we are going to likely want to use the empirical loss, which will measure the entire loss over our entire data set of all our predictions, as we don't only have our original single data point of view with a prediction and the actual, we have many more data from many more students who passed or failed the class, so we can get predictions for each of our inputs and compare them to our outputs using the loss function across our entire dataset with the method called empirical loss. And to do this for our probability problem, we're going to use a type of loss called cross-entropy. This cross-entropy loss is useful as we are comparing two different lists of probabilities. The first is a probabilities from 0 to 1, any real number, whereas our output is expected to be binary, either a 0 or 1 for fail or pass respectively. So at the bottom here, we can see that in TensorFlow, we use the tf.nn.softmax cross-entropy with logits between our actual expected values and the predicted values. Similarly, in PyTorch, we can use the torch.nn.functional.cross-entropy to get the difference between our predicted and actual expected outputs. So another type of loss we can use for different problems. So let's say we actually want to calculate the grade that you would likely get based on how many lectures you attend and how many hours you spend on your final project. So what we can use is a type of loss called mean squared error, which is used for models that we have continuous real numbers, meaning any real number outputted. So our percentage is going to be from 0 to 100 with any integer, and we can use the tf.square and tf.reduce mean for our loss in TensorFlow, so that way we can find the difference between our actual and expected outputs. And we can also use the tf.keras.losses.mse to shorten this operation. Similarly, in PyTorch, we can use torch.nn.functional.mse loss to find the difference between our predicted and actual outputs. So this is similar to our empirical loss function, but now it uses a square and a subtracting operation in order to find the difference between our two lists of predictions for our given inputs of the grade you will get on the final project. So now that we have covered why we need to train our neural network, let's get into the deep of how we are actually going to train it. So what we want to do is optimize our loss to achieve the lowest loss, which will be done by finding the best weights, so that way our loss function is at the lowest it can possibly be. So the closer to 0 our loss is, the better our loss is going to be, and meaning the higher accuracy our model will have. So we are going to do this by changing the weights. And remember that our weights are in a matrix format, so that means it's not one singular value we need to change. We need to update the entire list of weights for every input. So let's say for our previous problem, we have two inputs from 0 to 1 of a given probability, so W1 and W0 from 0 to 1, and we have our given loss from 3 to -3 graphed in this 3D graph. So the red points are going to be closer to a higher positive number, and the blue points will be closer to a lower negative number, whereas the green is going to be closer to 0. So what we want is to be as close to the green or to the negative value as possible. So first, we're going to randomly pick a starting weights for our initial model. So let's say we pick this crosshash mark here on one of the red hills. And then we're going to compute a value called the gradient, which is really just the derivative of our loss function with respect to the weights that we currently have. And that will tell us which direction is up, meaning which will give us a higher loss. And then we take a small step in the opposite direction, so that way we can get towards a lower loss and a higher accuracy. So we can repeat all of those steps, computing the gradient and taking steps in the opposite direction until we reach the lowest possible value of about -3. So overall, let me summarize these steps in a type of pseudocode where we're going to first initialize our weights values randomly. Then we're going to loop through computing the gradient, which is the derivative of the loss function, and updating the weights based on that gradient, and then returning the final weights after we achieve a loss with weights that we like. So we use this gradient by setting a value called the learning rate, which is an extremely small number that we use to scale down our gradient so we don't take too over-eager steps towards the right direction and instead take smaller, more careful steps so that way we don't overshoot and lead to extremely high weights and losses. So I'm going to be covering that process in more detail in the next couple of slides. So this algorithm of looping through computing the gradient and updating weights is called gradient descent. And we can implement this in TensorFlow code by first initializing random weights using tf.random.normal for a normal weight distribution. And then theoretically, we should be looping forever, but in reality, we cannot loop forever and we need to set a given amount of training iterations, which can usually be something like 5,000 or 20,000, depending on your application. So I see a question about having the derivative equal to 0 and seeing that we get to our minimum point while in a local spot, while the reality we are actually not in the actual most likely minimum. So that is actually a great question, as this often occurs in machine learning and deep learning when we set our learning rate to be too low and we get stuck in a local minimum where we cannot really get out of it, as usually our model will not go out, it will only go lower. And we usually solve that by optimizing our learning rate so that way we don't get stuck in a local minimum, whereas we don't overshoot and we just get an extremely high loss. So we usually do this by either optimizing our learning rate for our given model or using something called an adaptive learning rate, which I'm going to be covering in more detail in the next couple slides. So also I'd like to note that the derivative will never actually really equal 0 because there will always be an infinitesimally small value that you can always take a small step, which is usually why when you're finding the loss and you get to a minimum, it sometimes starts to oscillate back and forth as it is bouncing around in that local area, and it cannot really get anywhere lower as it can only go so low in that minimum, and it cannot really go out as that is not what neural networks usually do. So does that answer your question? All right. So back to our TensorFlow code for gradient descent, where we're going to loop forever, and usually we will not actually loop forever, but we are going to set a given amount of training iterations to loop through. And then we're going to use a method called tf.gradientTape, which is sort of like a tape recorder that will record all the operations we do within it in order to play it backwards or calculate the derivative of the initial input compared to our final output, so that way we can get our gradient and we can use it with our weights in order to shift the weights in the right direction. So first we compute our loss using a given loss computation function for our weights, and then we get the gradient by using the dot gradient function on our gradient tape for the loss function with respect to the weights, which is our step 3 of computing the gradient. And then we update the weights using a given learning rate of LR and multiplying it by our gradient, so that way our gradient can be shrunken down to a small usable size, and then subtracting it from the weights to move our weights in the right direction that allow us to have higher accuracy. So Now, there is going to be a problem with this gradient, as I've been talking about it quite a lot, but I haven't really been going into big detail about what it really is. So let's say we have this extremely simple neural network, a single input, a single neuron hidden layer, and a single output. So we can compute the loss for a given weight 2 between the hidden layer and our output by seeing how does a small change in that W2 weight affect our final loss. So let's use the chain rules to compute the derivative from the loss function all the way to that weight by computing the derivative of the loss with respect to our output, and then derivative of the output with respect to our W2, and multiplying those together to get that derivative for W2. And if we want to go all the way back to W1, the weight for the inputs, we can further apply the chain rule for W1 and map an extra output from the hidden state Z1 to the input. So that way we can finally have the loss for our inputs weights of W1, which we will now use to use a method called backpropagation, which was this method of going backwards, so we can compute our gradient and optimize the model. So for every weight that we have, as this is a simple neural network, we usually have much more neurons. So we're going to repeat this for every weight that we have in our network, and then use the gradients from the input layers, so that way we can optimize our inputs for the outputs. So now I'd like to cover the different methods of optimization that we can use to take our gradients and also compute our gradients, so that way we can have an efficient model that also quickly optimizes our loss. So the previous loss diagram that I showed seemed to be extremely simple, and it may make you think that it's a very simple process to train neural networks. On the other hand, it is actually extremely difficult. So this is a visualization of a given neural network's loss landscape from a paper from December 2017. So although their neural network was extremely complex and highly dimensional, they visualized their loss landscape like this, and you can see that there are a vast many of local minimum and maximum, as well as a large dip here, which is what we want to optimize to. But depending on where you randomly start, it can be extremely difficult to get there, as there are many other places to get stuck. For example, I see a hole there, or there, or there, and in so many places. So it makes it very difficult to train these neural networks to have the highest accuracy. So remember that we are going to be optimizing our model through gradient descent, where we calculate our gradient and use the learning rate. So now I'd like to examine how we set the learning rate, so that way our loss function takes the right amount of steps towards a higher accuracy while not getting stuck anywhere or overshooting to an extremely high loss. So if we set the learning rate to be too small, then if we have an initial guess at this point, red point, we want to get to the star, it will converge in a small local minimum, and it will pretty much get stuck there and be unable to ever reach the star. So there is an extremely small dip around here, and the point would go towards here with its gradient and then start to get stuck there without moving on to the actual wanted loss. On the other hand, if we use very large learning rates, then the model will start to shoot back and forth very rapidly until eventually it reaches a very high loss, and the model training does not really have any effect. If we set a stable learning rate, which is the best of both worlds, then it will quickly, the initial guess of weights will quickly get towards our star point and start to oscillate there until the end of its training, where it will get the best possible loss at our star point to have the highest accuracy for the model. So now you may be wondering how we are going to find this optimal learning rate, and there are two different ways. So first, we can try many different learning rates and see which one works the best, which can sometimes be time consuming and also will take a long time to test and see the output and test and keep looping through that testing. Whereas we can sometimes do something smarter and design something called an adaptive learning rate that changes depending on how far you are from the optimal loss, adapting to the loss landscape. So that means that our learning rates are no longer fixed at a specific value, and they change throughout the entire training process, and they will change to be larger or smaller depending on the size of our gradient, how fast our learning is approaching a given correct loss that we want to achieve, and the size of the given weights that we currently have, including the size of the matrix as well as the actual values themselves. So in code, there are many different gradient descent algorithms, including stochastic gradient descent, or SGD, which is a method of gradient descent that doesn't train on the entire dataset and only uses specific parts of it. So I'm going to be covering stochastic gradient descent in the next couple of slides. But you also see that there are several different optimizers like Atom, AdaDelta, and AdaGrad, and this ADA at the beginning of each stands for its adaptiveness, meaning that it does use adaptive learning rates in order to achieve higher accuracy. So throughout the TensorFlow and PyTorch implementations, we can see that each one is extremely similar, with TensorFlow having tf.keras.optimizers and the name of the optimizer for each one, and similarly, PyTorch has torch.optim. The name of the optimizer you want to use. And when implementing code to train a neural network, it is often as simple as changing a single line in order to change the optimizer you are using to change the different optimizer that you're having to see what effects it may have on your training process. And we're going to implement some code in TensorFlow for a given optimizer of our stochastic gradient descent. So first, we define a model with the tf.keras.sequential API with however many layers we like in whatever architecture we want to use. And then we can pick our optimizer. So right now we're using SGD, but we can use any optimizer like Atom or AdaDelta. And then we can loop through our training process to get our predictions from the model and use the gradient tape to compute the loss with our given loss function between the actual outputs and our predictions. And then we can calculate the gradient for our loss with the model's hyperparameters, which are how we're going to set it, which are the values that dictate how we're going to set up our model. And then we can use our optimizer to apply the gradients to our model, also with the hyperparameters, so that way our model stays the same in its architecture while changing its weight slightly to have a higher accuracy. So now I'd like to introduce the concept of using mini batches, as whenever you are training with normal gradient descent, it can sometimes be very computationally intensive to compute the gradient for our entire dataset, as datasets are often extremely large. So we can use a sort of naive method of only taking one single random data point from our entire dataset and computing the gradient for this given data point. Now, this allows us to have an extremely fast computation and will significantly speed up our training process. But unfortunately, this is very stochastic or noisy, which means that the gradient that is calculated for our specific data point will not reflect the entire data set and will usually lead to a very low accuracy on testing data sets that are in the real world because of this extremely small scope of training. So as a middle ground, we can take a batch of given data points and then compute the gradient for that batch. So we will take a given amount of data points, so let's say 32 data points from our entire data set, and we will calculate the loss for each of these data sets and then sum them all together to get our gradient for that given B data points of our batch. So now this is still fast to compute and has a much better estimate of the true gradient than the entire dataset training would have, while also having a higher accuracy than only picking a single data point. So this method of using a batch is called stochastic gradient descent, as only training on specific parts of the dataset is called stochastic, as it's not looking at the entire dataset, but it's still looking at parts of it randomly in order to achieve higher efficiency while still allowing it to have higher accuracy on new data that it has not seen before. So again, with these mini batches that we can use in training, we have a more accurate estimation of our gradient compared to using the entire training dataset, as well as a better convergence towards a lower loss. And we can also now use larger learning rates, as we can now trust our gradient value more since it is a better estimation, and we can allow it to take larger steps towards a higher accuracy loss. Furthermore, these mini batches can allow us to significantly speed up training, as each batch has its own mathematical operation that can be parallelized using GPUs, which will allow us to significantly increase our speed as well as have higher accuracy for our model. So now we have covered mini batches and how to create neural networks and train them. I'd like to cover an issue that we sometimes encounter called overfitting. So first, I'd like to introduce the concept of underfitting as well. So when our model is not trained enough on our entire dataset, we do not usually get a full prediction of the best of its ability. So if we have this nonlinear trend, underfitting would be having a poor representation of this data or a linear line that does not fully capture every data point. On the other hand, overfitting is when the model is trained for too long and it has too complex of a relationship, and it starts to sort of memorize the data it was trained on, trying to exactly perfect its fit. Ideally, we would like to have a general fit that is in between these under and overfittings, where we have a good trend of our training data, but this trend will also work on never before seen data in order to make accurate predictions. So to solve this issue of overfitting, we use a method called regularization, which allows us to constrain our optimization so we don't have these complex models that lead to overfitting. We especially need this because we need to improve our model's ideologies that it has on data such as the testing data in unseen environments that have never been looked at before. So an example of self-driving cars, if we train our AI model for the car on images of different roads, we would need regularization so that way it can understand new roads that it will be driven on while not crashing or starting to burst in flames when it hits the side of the road because it overfitted to its training dataset and does not understand the new testing data. So the first method for regularization is called dropout, which is where we sort of deactivate some of our neurons from our hidden layers by setting their gradients to 0. So usually we drop about 50% of any of the neurons in our layer, which allows our network to sometimes be prevented from relying on any specific neuron that we have in our dataset. So to do this, we create a layer of dropout. In TensorFlow, we can do this by tf.keras.layers.dropout and set our p parameter for how many neurons we want to drop. And similarly, in PyTorch, we can use torch.nn.dropout and set our p-value to see how many we want to drop. So we continuously keep randomly dropping our neurons throughout the hidden layers, so that way their gradients are completely unallowed to train on the rest of the dataset while allowing the rest of the neurons to move forward and make sure that our neural network does not consistently only rely on one neuron while not accepting inputs from the rest. So another method that we can use is early stopping of the training, where we stop our training before it has the chance to overfit on the training dataset. So let's say we have this loss landscape between the training and testing datasets where they both start very high and they go down significantly during our training iterations. They continue the same trend for a while, but eventually the testing loss starts to go up while the training loss continues to go down. So our training loss will never ever go up until it starts to reach its local or global minimum, and then it starts to oscillate a little bit as it cannot really go any further. But usually our testing loss will start to go up while our training loss will start to go down as we are overfitting. So we see this trend continue where the testing loss starts to go back up while the training loss just keeps going down. So what we can do is stop the training at the best possible place that we had for our given testing. So we do this by saving the weights at regularized intervals throughout the training and testing processes, so that way we can see where the testing dataset has the highest accuracy with the lowest loss, so we can stop training there, take those optimized weights, and use them in order to have our model with the best accuracy in the real world. So in this case, anything before our stop would be underfitting, as the model still has the capacity to have higher accuracy, whereas past it would be overfitting, as our model starts to have higher accuracy on the training, while not having a higher accuracy on the testing, as the training dataset starts to overfit and our model starts to have problems. So in conclusion, we covered what the basic neural network is through the perceptron and covered why we need it, as well as why nonlinear activation functions are so critical for neural networks. Okay, so I see a question about our random dropout. So let me go back to that slide. So in Dropout, randomly dropping the neurons will not always hurt the optimal neurons, as it only drops them for one training iteration. Because although neural networks have many neurons, if we continuously keep dropping the neurons and leave them dropped, we will eventually have no neurons left. And we definitely don't want that, so we randomly drop them only for one iteration. So if we have one iteration for this training, we only drop out these 3 neurons, whereas in the next step, we will drop out these 3 neurons, and all neurons will still be given a chance to contribute their gradients towards a higher accuracy. So although it may occasionally hurt the optimal neurons if they are randomly cut off repeatedly, it usually does not happen, and our neurons with the optimal predictions are always still given some influence on the final outputs. In neural networks, we saw how we can stack our building blocks of perceptrons to create deep neural networks with many layers, as well as how we can optimize them using the backpropagation method of computing the derivative of all of the weights from our loss function, so that way we can optimize our neural network to have the best weights with the highest accuracy. Then we saw how we can actually train our neural networks in the real world by using things like adaptive learning rates, mini batches for higher accuracy and efficiency, as well as regularization to ensure that our model performs the best on its real world data. So along with this deck of slides, we have a lab that goes along. So I see that we have another question about the optimal point of choosing for the overfitting for our global minimum. So in overfitting, we do look for the best loss that we achieve during training, but it is usually not always going to be the global minimum. So during training, we see a variety of loss values, and where we stop the training is going to be where the loss is at its best. So in overfitting, if the best loss we achieve is at the global minimum, then yes, that's where we're going to stop training. But usually we just stop the training at the best loss that we achieve to have our best accuracy while not overfitting on the training dataset. The lab that is associated with this lecture can be found on the AI Program Labs button in the inspiredk.org website. So if we go click on that button, we will be taken to the inspiredk.org GitHub page, where you can navigate to the MIT Intro to Deep Learning directory, and from there, the Lab 1 folder. From there, you can go to the Lab 1.1 Introduction to TensorFlow lab, or the Introduction to PyTorch lab, so you can gain a deeper understanding of both the TensorFlow and PyTorch libraries, as well as their syntax to implement them in Python. So as you go through this lab, as well as the others, you will have several different to-do blocks where you will be required to fill out different parts of the lab, so you can make sure that your understanding is concrete and you understand how to implement these technologies in practice. So if you ever need help, these solutions can be found in the solutions directory of Lab 1. And there are also going to be lab explanation videos that go along with each lab for both TensorFlow and PyTorch. And currently, the Introduction to TensorFlow lab explanation video is posted on the inspiredkey.org website. So if you scroll down all the way, you will be able to watch the video to, if you ever get stuck, to understand the lab and see how to implement it in practice so you gain a deeper understanding of these technologies.